Okay, so this is our last section of notes for Unit 5, and we're going to ask the following question, that if we can find the mass of a mole of atoms from a single element, can we find the mass of a compound, so the molar mass of a compound? And if we've got 1 mole of water, we know that that's 6.0221 times 10 to the 23rd water molecules, and that if we toss that on a scale, it's going to come out to give us 18.02 grams. Well, can we figure that out without actually having to go to the scale? Sure we can. Let's just look at the water molecule. It's just a combination of oxygen and hydrogen atoms. So if we know the molar masses of each of those atoms, which we do from the periodic table, then the math is quite simple. The 18.02 comes from the adding of the masses of the individual atoms. Hydrogen is 1.01 grams. You'll always notice that I round hydrogen up to 1.01, although in the periodic table it's often 1.0079 or something like that. So hydrogen is 1.01 grams per mole. You've got 2 moles of that in every 1 mole of water, so we're going to multiply it by the 2. And then we only have 1 oxygen atom in the molecule, so we've got 16.00 grams per mole in every 1 mole of water molecules. And so we just do 1.01 times 2 and 16 times 1, and then we add them up, and we get 18.02 grams per mole. I'm such a stickler for significant figures, I'd be a bad teacher if I didn't point out what it is and how I wanted significant figures for this particular issue. Let me grab a highlighter here. There we go. All right, so you'll notice that each one of the molar masses that I take are always going down to the second decimal place. If you look on the periodic table, some molar masses are known to a more degree of certainty than others, but that varies from periodic table to periodic table. So for consistency in this class, we are always going to go down to 2 decimal places in our molar masses. So that doesn't only apply to the molar masses of single elements, but that also applies to the molar masses of complete compounds. All right, so let's look at something a little bit more difficult. Let me go back here. There we go. Calcium phosphate. So calcium phosphate's a compound that we use to make fertilizers. The phosphate ion in the back, the PO4 stuff, is important in fertilizer usage. So let's try to figure out how to find the molar mass of one of these guys. If we have one little calcium phosphate molecule floating around, which you'll find out a little later on is impossible, but let's just say that we had one floating around, we'd want to know what the molar mass of it, or an entire mole of it, would be. So we have to break it down. We have to find the numbers of each individual atoms. Well, how many calcium atoms we have? We have calcium, which has a molar mass of 40.08 grams per mole, and there are 3 of those. So we'll go ahead and multiply that by 3. The 3 comes from the subscript right there in the formula. We also have phosphorus. Okay, that's P. P is phosphorus. Now this is kind of tricky. You have to kind of remember your distributive law in algebra class. See this 2 that's outside of the parentheses? That kind of gets distributed through the entire PO4. So you're going to take that number and multiply it by any subscripts that are inside of the PO4. Well, the subscript that's after P is nothing, so it's a 1. So we just take the molar mass of phosphorus, which is 30.97 grams per mole, and the formula tells us there's 2 of them. We multiply it by 2. And then we'll do oxygen last. There's actually a lot of oxygen atoms in this particular compound. Okay, again with that distributive property, you're going to take that 2, multiply it by the subscript, so 2 times 4. That's 8, right? So you take the molar mass of oxygen, 16.00 grams per mole, and you'll multiply that by 8. And when you're done, you'll take all of these numbers and you'll sum them up. You'll add them all up. And you're going to find at the end of the day that your molar mass for calcium phosphate is 310.18 grams per mole. So again, what does that mean? Well, if you have calcium phosphate and you put 310.18 grams of it on a scale, you know exactly how many calcium phosphate little tiny molecules there would be floating on your scale. Okay? All right. So last thing then, if we now know how to computate the molar masses of compounds, we can figure out, if we have a particular compound, what's the percentage of each element in that compound based upon molar mass. Now, we've done this before based upon mass, upon grams, but never on molar mass. So the percent of each element in a compound is totally independent of the amount of material. 1 gram of water has the same percent of hydrogen and oxygen as 16 grams of water. It just doesn't, as an entire ocean of water. Okay? So totally independent of the amount of material. And we're going to look at my favorite molecule as our example. This is caffeine. So in caffeine, there's 8 carbons and 10 hydrogens, 4 nitrogens and 2 oxygens. And I might ask you, okay, calculate the percent composition of each element in this compound. And the first thing that you're going to want to do is calculate the molar mass of the entire compound. And if you do that, and you do it correctly, you'll figure out that its molar mass, usually abbreviated mm by the way, is 194.19 grams per mole. Now, if you want to figure out the percent carbon in your sample, you take the carbon atoms, just the carbon atoms, so that's 8 carbon atoms, find the molar mass of those 8 carbon atoms, so what would that be now? 12.01 times 8, right? So that's 96.08. You divide that by the total molar mass of the compound, so that's 194.19 grams per mole. And both of these are grams per mole, by the way, and that will show you that they actually do cancel out. Go on. Okay, always unit analysis, right? It's always a good way to go about things. And remember, we do want a percentage, so let's go ahead and multiply our final answer by 100 to get a percentage. I'll have to calculate this out for us. Let's see, 96.08. And let's divide that by 194.19. And my calculator tells me that that's 49.48%. So this compound is 49.48% carbon. So if you had 100 grams of caffeine, 49.48 grams would be devoted solely to the carbon atoms. All right, now there's 3 other elements in this compound. I'd like you to go ahead and try to figure out the percentages of each one of those, and if you do it correctly, what should all of those percentages end up adding up to? Hopefully you know that should be a hundo. Okay? All right, that's it.